Parity is a but powerful method for ensuring data integrity and reconstructing lost data in binary storage schemes. I think this is best illustrated with some examples, but before looking at the examples, parity can be either even or odd parity. Which of the two you implement doesn't matter, they both achieve exactly the same end goal with the same overheads. In our examples, we'll use even parity. Even parity works by making sure that there is always an even number of ones in a row of data. We'll use a 4-bit dataset here, with the last bit in each dataset being used as parity. So let's look at our first example. Here we've got 3 zeros. So in order for there to be an even number of ones in our dataset, the parity bit must also be a 0. If it were a 1, we wouldn't have an odd number of ones. Great! Let's look at another example. This time our dataset has a single 1, so our parity bit must also be a 1, giving us a total of 2 ones, or more importantly, an even number of ones in our dataset. Pretty simple stuff, but let's go through a few more examples just to solidify the point. This time we already have an even number of ones. We've got 2, so the parity bit must be a 0. This time we've got an even number of ones again, so our parity bit is again a 0. And one last example. This time we've got 3 ones, obviously an odd number, so to ensure that we have even parity, our parity bit must be a 1, giving us a total of 4 ones, even parity. Cool! Or maybe boring, depending on what gets you excited, but this is really important. It's fundamental to many RAID levels, and it allows us to be able to lose a single drive in a RAID set and not lose data. We don't lose data because we can recalculate what the contents of the lost drive were based on our use of parity. So let's go and do it. Look a little closer at the picture of our 5-drive parity set with a failed drive. Because we're using even parity, we know that all of the rows in the diagram must have even parity. With this knowledge, we can determine what the missing data in each row is. So on the top row, we can see that we've got 3 zeros and a single 1. This is an odd number of ones, so we know that the missing data must be a 1, otherwise we wouldn't have even parity. The middle row has 3 ones, which again is an odd number of ones, therefore the missing data must be a 1 in order to bring us to an even number again. And finally, the bottom row has an even number of ones, meaning this time the missing data on the bottom row must be a 0, otherwise we'd have an odd number of ones. Simple, but massively effective, at least effective at recovering from a single drive failure. Double drive failures are different, and they require double parity or 2 sets of parity. The net result being a small loss of usable capacity for the ability to ride out a single drive failure.